Good day, everyone. My name is Owen Lewis, and it's a pleasure being here with you to talk about nuclear fusion. I know it's a bit of a different topic from what you're used to at this conference, so thank you for coming to listen. Quick bit of background. I like to think of myself as a fusioneer, someone who advocates for and works towards bringing practical and economic fusion energy to fruition. I'm actually a geologist by training and work in the oil industry here in Calgary. As many of us do, I have a keen interest in science and space. Fusion started out to be a serious thing for me a few years back, and since then I've learned a lot about it and been fortunate enough to have some opportunities like today to explain a little bit about fusion and its potential. Today I want to talk to you about what nuclear fusion is, a bit about the pros and cons of fusion, and look at what sorts of machines are being built and fuels used, and how much progress has been made. Lastly, we'll talk about what governments are doing and the incredible progress that private fusion companies have been making recently. Some fusion history. So the first paper ever published on fusion was by British astrophysicist Arthur Eddington. At the time, his proposal that the sun was powered by the fusion of hydrogen into helium was paradigm shifting. The current theory suggested that the source of the sun's light was heat given off by gravitational contraction. During the presentation of his paper called The Internal Constitution of the Stars in 1920, he remarked that a star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, which it is known exists abundantly in all matter. We sometimes dream that man will one day learn how to release it for use in his service. The store is well nigh inexhaustible, if only it could be tapped. As you can see, we've been at this for a while, and while creating a fusion reaction is actually relatively easy, teenagers have literally done it in their garage. Getting more energy out than we have to put in to make the reaction go has proven elusive. At this point, it might be helpful to explain the difference between fission and fusion. Now, I'm sure all of you already know this, but if it comes up in conversation, it's good to be able to clearly and simply state some of the key differences. So fission and fusion are both nuclear processes. That is, they have to do with reactions which occur in the nuclei of atoms. Both convert mass into energy, as described by Einstein's famous equation, E equals mc squared. Fission takes a large atom like uranium or thorium and uses a neutron to split it into smaller pieces, yielding a large amount of energy in the process. Fusion does the opposite, taking two smaller atoms like hydrogen and fusing them into a larger one like helium, again with significant energy being released, around 3 to 4 times the amount that you get from fission. But of course, forcing the nuclei of atoms together is difficult. The sun fuses hydrogen into helium by starting off with 4 protons, and through a series of steps creates about 0.7% of the mass of the original protons into energy, with the end result being helium and a ton of energy. On Earth, this proton-proton chain the sun uses is too hard. The reaction simply won't happen frequently enough at reasonable temperatures and small enough containers to be practical. The sun gets away with it because it's so incredibly huge. Its massive size lets it use gravity to create fusion conditions in its core, but unfortunately that's not possible to do here. So we weight the odds in our favor a little by using heavier isotopes of hydrogen. We use deuterium, which is a proton plus a neutron, and tritium, proton plus 2 neutrons. This DT fuel is usually considered the easiest to work with because it fuses at relatively low temperatures, around 150 million degrees Kelvin, only about 10 times hotter than the sun's core. Only. Deuterium for use in DT fuels has the advantage of being abundant. It's literally extracted from seawater, where it makes up about 1 out of every 6,420 hydrogen atoms floating around. The tritium is trickier as it's actually mildly radioactive with a short half-life of just 12.3 years, so it doesn't exist naturally, not really. It can, however, potentially be bred or created from fusion-produced neutrons interacting with a lithium blanket surrounding a fusion reactor core. There's significant work being done to figure out the best way to do this. Currently, most tritium comes from existing nuclear fission plants, particularly CANDU reactors. Okay, let's talk about the pros and cons of fusion. On the pros side, fusion is the holy grail of energy, generating significantly more per kilogram than any other source within our grasp, including nuclear fission. Fusion fuel contains over 1,000,000 times more energy per kilogram than coal and natural gas, and at least 3 to 4 times the energy in fission fuel. It depends exactly what kind of fusion fuel you're using. As an added bonus, the fuels used are generally abundant, essentially inexhaustible, and would allow the production of electricity without CO2, particulates, or other undesirable byproducts being emitted into the atmosphere. In other words, clean, abundant, and reliable energy. Fusion would be safe. There's zero chance of an explosion or meltdown because, unlike nuclear fission, a fusion reaction will not just carry on by itself on Earth. As we mentioned before, base fuels are generally abundant. There's some caveats with this, but there's good plans for dealing with that. It's sustainable, fusion is, because we'll essentially never run out. We can generate massive amounts of energy with minimal impact on the environment. Moving beyond the abundance of fuel, fusion will allow the production of abundant, virtually unlimited energy. While the first few commercial reactor prototypes will, of course, be expensive, fusion has the potential to be quite affordable. There's been a few papers published that have given estimates for fusion energy as being quite cost competitive, potentially in the $40 to $50 per megawatt hour range. Even if prices are ultimately higher than this, it could help make the grid as a whole cheaper, particularly the advantages of providing always-on power and reducing the need for expensive infrastructure investments like long-distance transmission lines. Reliable. Fusion will share this characteristic with existing nuclear power plants, as well as natural gas and coal, in that it won't be weather dependent, which is a huge drawback for renewable energy like wind and solar. Not that fusion will overnight be able to replace renewables, or traditional energy sources for that matter, but it has all the pros of both traditional and renewables and very few of the cons. Another thing that fusion energy will do is continue improving global standards of living. During the past couple centuries, we've seen massive improvements in every standard of measure for human well-being. All of this ultimately hinges on energy. Abundant, reliable, affordable energy is the base on which almost everything else good is built. Some of the biggest applications in developing fusion will undoubtedly be in its space applications. One of the underlying reasons everything is difficult for space transport is the time it takes to get anywhere. Even the moon is a 3-day trip one way. Going anywhere interesting past that, and you're looking at months, if not years. The travel time increases the amount of food, water, and other supplies you need to bring along. And the longer you're traveling, the greater amounts of radiation you're exposed to. Basically, every single aspect of spaceflight becomes easier the shorter the flight is. Fusion propulsion will allow us to get from A to B faster. A first-generation fusion rocket could likely take a 6 to 8 trip one way to Mars and cut it down to a couple of months, maybe less. Being able to do faster trips with larger ships opens up all sorts of possibilities in the solar system, like asteroid mining and settling permanently on Mars and elsewhere, perhaps even terraforming Mars one day. Another good point to mention is that a civilization capable of mining asteroids is also going to be capable of finding and moving the dangerous ones which could otherwise hit us. The last point on space is that fusion-powered rockets could allow us to travel to nearby stars within a human lifetime. Fusion rockets could accelerate us to maybe 10% the speed of light. Trips would be long, but doable. To reach the nearest star system, Alpha Centauri, would take just over 40 years at these speeds. Long, but possible. So nothing is perfect, unfortunately, and sadly, fusion is no exception. So the biggest downside is also the most obvious. Nobody's made it work yet, not economically. There's been incredible progress, but so far nobody has managed to get more energy out than was put into making the reaction go. As I said earlier, one of the most common planned fusion fuels is deuterium-tritium. Deuterium is abundant, but tritium is rare, mildly radioactive, and has a short half-life. The current sources are nuclear fission power plants, but the amounts produced are small, not enough for ongoing commercial fusion operations. The biggest difficulty with DT fuel is that around 80% of the energy from the reaction is in the form of high-energy neutrons. These have the unfortunate effect of slowly turning materials they interact with radioactive, necessitating replacing parts of the reactor every few years, as well as shielding around the reactor core. Thankfully, though, both the radioactivity from tritium and as a result of high-energy neutrons is fairly mild, requiring storage for only a few decades as opposed to centuries or millennia with traditional nuclear waste. Another problem is cost. The world's biggest fusion experiment, ITER, the International Thermonuclear Experimental Reactor in France, is way over budget and behind schedule. Final costs may be up to $50 or $60 billion US, potentially. This is mostly an issue with this specific project, but unfortunately it's taken up the lion's share of money directed at fusion for the past couple of decades. You may have heard that fusion is perpetually 30 years away. In the past, there's been a lot of truth to that accusation. Fusion was harder than expected, and some of the technology needed to make it work in a practical way simply hadn't been invented until recently. The last big issue has actually been a chronic lack of funding. As you can see from this older graph, funding to develop fusion in the United States pretty much stayed below the estimated fusion never line. A lot of that money has gone into ITER since early in the 2000s as well. This has changed in the last few years, the last couple particularly, but overall levels of government funding are still low, particularly compared to what gets put towards R&D for renewables. A quick note on fusion reactions. The reason why DT fuel is so popular is the relatively low temperatures needed to have good reaction rates, so about 150 million degrees Kelvin. There are other possible fuel avenues for fusion, however, though they require higher temperatures. The advantages of these other fuels is less neutrons, which means less or essentially no radioactivity, direct generation of electricity, and the simplification of several other problems. Ultimately, you end up with a smaller, cheaper machine. The majority of private companies and big government projects like ITER tend to favor DT, but some go other routes, including deuterium helium-3, and a couple plan to use proton boron 11 fuel. Not going to go into a lot of detail here, but just wanted to show you that there are in fact a variety of approaches being pursued when it comes to reactor design. There's the most traditional, tokamaks and stellarators, which have historically had the most funding, especially tokamaks. ITER is a tokamak. They fall into the category of magnetic confinement fusion. So you're taking powerful magnets and shaping the plasma and compressing it with those magnets to fusion conditions. Both are toroidal or donut-shaped devices that use magnets to confine and stabilize the plasma that will undergo fusion. Then you have inertial confinement fusion, which can use lasers like the National Ignition Facility, NIF, in the USA. Not all variations on this use lasers. Some use an approach that fires projectiles into a capsule of fusion fuel, compressing it to fusion conditions. These other approaches that I put here are mostly just to show you the diversity of approaches to reactor design that are being taken. What we're looking at here is called the Lawson criteria, also commonly called the triple product, because these three terms are commonly used to gauge fusion's progress towards energy break-even, which is where the energy produced by the reaction is equal to the energy expended in making it occur. This shows various fusion projects, including ITER's projected value and that of a machine called Spark, which will be built by a private fusion company. Both will be just shy of what you need for true commercial operations. So the three triple product terms that we consider here are plasma density, so it's the fuel density, the energy confinement time is for magnetic confinement, or pulse duration for inertial confinement, and the plasma temperature, so the fuel temperature. The goal is to reach energy break even and eventually energy gain, which is where you end up with more energy out than it takes to run the reaction. This term is generally denoted as Q. When Q reaches about 1, you're producing enough heat to keep the reaction going, more or less. There's different types of break even. First up is what's often called scientific break even, which is just about the plasma, but ignores all the other power requirements. Next is engineering break even, which is where you're producing enough energy to actually, electricity rather, to actually run your machine, not just to heat the plasma. The ultimate goal is economic break-even, which is where you need to be in order to make commercial fusion power plants a reality. So Q equals 1 is the starting line, the Kitty Hawk moment. So what's happening now in terms of what governments are doing? The world's largest fusion project, ITER, is a tokamak being built in the south of France. It broke ground in 2007. Its objective is to provide a testbed for fusion technology and eventually produce net energy gain of 500 megawatts thermal from 50 megawatts electrical input. ITER won't actually produce electricity, but is intended to serve as a precursor to an even larger tokamak called DEMO, the demonstration power plant. This in turn will show fusion is capable of producing electricity and help inspire the design of more efficient and economic power plants. All that sounds great until you look at the timeline and cost. Currently under construction, ITER won't start plasma tests until at least 2026, or DT fusion before 2035-36. Demo operations are slated to begin in the mid-2050s. Cost overruns and delays have plagued ITER, with costs ballooning from the original $7 billion up to tens of billions, making it the most expensive scientific endeavor in history after the International Space Station. Several governments aren't interested in waiting another 30 plus years for demo to prove itself and have started their own programs with accelerated timelines. In 2020, the Department of Energy in the States published a report calling for public and private investment in an American-built fusion power plant, with the goal of starting to provide electricity to the grid by 2040. Around the same time, a bipartisan fusion caucus was formed. As well, the annual budget for fusion research was recently increased. Over in the UK, the government has recently set aside about £700 million, and it's about 860 million USD for their fusion program, which has a goal of a prototype plant producing electricity by 2040. Nor are Western governments the only ones pursuing fusion. China is designing their own tokamak, which has two phases that parallel ITER and demo, but with a faster timeline. Plans aim for completion in the 2030s and 2040s, respectively. Japan has recently launched ambitious fusion plans as well. It's worth noting that NIF, the National Ignition Facility in the States, recently achieved ignition last year, or very close to it. That's the point at which fuel generates enough energy to keep the reaction going. It doesn't count all the energy it takes to power the lasers, and NIF wasn't designed to be a power plant, but still, it's a step in the right direction. So there's been a lot of encouraging progress in the private sector for fusion in recent years, including an explosion in the number of private fusion companies and in the variety of their approaches. There's around 35 companies at the moment that together have managed to attract around 4.4 billion in private investments at last count. A paltry sum compared to expenditures in renewables or even ITER, but a huge increase over the almost non-existent money a decade or so ago. There's now even a Fusion Industry Association, which was founded in 2018 to help the nascent fusion industry speak with an amplified voice and to begin working with governments on regulations suitable for fusion energy. Another recent interesting news story was from Commonwealth Fusion in the States, which has successfully tested their new high-temperature superconducting magnets. These will let them create stronger magnetic fields and ultimately build a smaller power plant, which saves money. At the moment, it's difficult to pick which companies are leading the pack or have the best reactor designs and concepts. We can approximate progress by looking at who has managed to raise the most money. These include TAE Technologies, Helion Energy, Commonwealth Fusion in the States, and Tokamak Energy in the UK. Another promising company is General Fusion in Canada. Most of these large companies believe that they will have their energy break-even moment this decade, and aim to have a commercial prototype providing electricity by 2030 or shortly thereafter. Whether these companies will succeed in these timeframes remains to be seen. It's worth noting that there are also a number of smaller fusion startups with significant potential as well. So oil and gas companies have, as we all know, started to evolve from dealing only in hydrocarbons into energy companies more broadly. Some of the large ones have actually started to invest in fusion companies. I've got 4 that I found listed here. So it's a small start, but personally, I find this quite encouraging to see. Our industry knows energy, so nobody is better positioned than us to help push fusion forward towards commercial reality. I think that fusion will be a big part of the future of energy, so why shouldn't the oil and gas industry be part of it? Let me end by summing up some of the changes which have allowed this acceleration of fusion development. Several factors likely played a role, including more powerful computers and plasma modeling software, high-temperature superconductors, which have allowed stronger magnetic fields, better plasma confinement, and ultimately cheaper machines. The biggest change has probably been funding. ITER aside, fusion R&D really has been on a starvation budget for decades. Indeed, it's remarkable that as much progress as has been made was even possible. That this has begun to change in recent years has propelled progress forward. It's hard in such a short space to give an overview of what's happening in fusion, especially the private fusion industry, or to properly convey the renewed sense of excitement and optimism. There's still a lot of work to be done, but fusion energy is now a question of when, not if. and the when could be coming up a lot faster than most people realize. As someone who's been watching the space closely for the last few years, my personal estimate is that we'll see prototype commercial reactors being hooked up to the grid and starting to generate electricity by 2030, 2035, possibly sooner. I could be wrong, but that's my guess. Nuclear fusion remains a relative unknown in the oil patch. Hopefully this presentation has helped serve as an introduction to this emerging industry. All right, well, that's it for my presentation. Hope you all enjoyed it. I want to thank the GeoConvention and the session organizers for letting me present on this. If anyone has my questions, I will do my best to answer them.